This video details the SweetPhotos project, in which we have created a binary classification convolutional neural network to predict if a sweet potato meets the ideal U.S. Department of Agriculture grading standards or not. The team consists of 3 North Carolina State University students, Jordan, Enrique, and myself, Shelley. This work is a part of the larger SweetApps research project, an NC State-funded research initiative using big data analytics and optical scanning methodologies to increase crop quality within the North Carolina sweet potato industry. Myself and Enrique are both graduate students on the SweetApps team, and Jordan also has interest in agriculture and works within the industry. Sweet potatoes are a root vegetable packed with many nutrients and vitamins that have become a staple of North Carolina crop production and export. Grown underground, these tubers tend to have variable shape and size. The value of the crop is highly dependent on the grade, or a USDA-defined classification based on size. Grading standards are a few decades old and slightly vague, leading to inconsistencies in classification. There exists a need for a non-biased, standard means of classifying size and shape in a timely manner. Past studies created methodologies of scanning and characterizing crops, but all were too time-consuming, with no easy way of integrating into standard packing procedures. Dr. Samuel Hawk, a graduate from the North Carolina State University, was the first author of a paper presenting a novel approach to quantifying crop size and shape characteristics using high-throughput imagery, equipment already available to most of packers. The authors created a computer vision algorithm that utilized 2D images of scanned sweet potatoes to create a 3D model of the root and estimate key quantified shape features. The 2D images were labeled by domain experts into 2 classifications, good or cull. With the good potatoes meaning grading standards for US number 1, the most valuable grade. Hawk then created a variety of machine learning models to predict shape classification based on the estimated shape features extracted from the images. The objective of this study is to create a convoluted neural network model using 2D images of scanned sweet potatoes from on-farm high-throughput imagery equipment to predict shape classification. The aforementioned study by Hawk created predictive models using a tabular data set derived from these images, whereas our inputs will be the images themselves. The same exact images utilized by Hawk and his fellow authors will be used to train and test our neural network. Images were captured from an Exeter scanner on the NC State and USDA Agricultural Crops Research Station in Clinton, North Carolina. The sweet potatoes were used in the study, were grown there in Clinton in the 2018 season as part of the sweet potato breeding program. So there are hundreds of different types of cultivars or clones. The images looked like the scanned sweet potato displayed here. The scanner captures 2 views of a single potato rotated 90 degrees due to mirrors located below the camera. The raw images are grayscale with the width of 768 pixels and a height of 1024 pixels. Originally, there are 1,349 images in total, with 622 labeled as good and 727 labeled as cull. As the majority of each image was a dark background of the conveyor belt, we cropped each image to remove some of that useless information. The images were then scaled down to 128 by 128 pixels, and the batch size was set to 20 to use less memory while still preserving a reasonable amount of detail in the images. We increased the size of our data set and balanced the data by performing data augmentation. This just means we duplicated photos and made a few adjustments here or there to help generalize our model and increase its predictive capability. These data transformations included clockwise rotations, anti-clockwise rotations, horizontal flips, vertical flips, and the addition of some random noise. This image here shows a few examples of what our augmented data looked like. The network architecture is shown here in this helpful diagram. On the left, we see the representation of our input image, which is a 128 by 128 pixel image with 3 channels. A 5 by 5 kernels with a stride of 1 is used, which results in a 124 by 124 pixel image. The image is then pulled with a 2 by 2 kernel. Our image is flattened into a very long vector, which is passed through a fully connected network. Our output is represented by the 2-dimensional figure on the far end, indicating our final prediction will be one of 2 possibilities, good or cull. Results indicate that our model boasts a 99% accuracy. An accuracy of 100% would mean perfect performance, and that our model could always distinguish between a cull and good sweet potato. This is a little suspicious, and with this high of an accuracy, we are worried about potential overfit. Here we see the learning curve for our model. Over the training iterations, the parameters within the model optimize to reduce our cost or loss function. If you have an overfit model, you would see your training loss decrease, but your validation loss increase. Your model wouldn't generalize well and would not perform great with new data. We don't exactly see this happening. In fact, our validation loss continues to decrease. Observing the accuracy by class, our model was 100% accurate at predicting the shape good and 99% accurate at predicting the shape cull. You can see this represented here with the confusion matrix heat map. This graph showcases our number of correct classifications and a few misclassifications. Most observations fall along the diagonal, indicating that the images were mostly correctly classified. Although our model technically outperformed the baseline, we note that our model is less robust of the two, and there might be some underlying issues that we have not discussed. Thank you so much for watching this videos, and our emails are listed here if you have any questions. Thank you.